Tower of Hanoi, one of those classic examples in computer science. Um, I mean, it's kind of a easy problem once you understand it. But I remember the first time I heard it, it sounded very easy to do in practicality, but hard to like program. Try to like wrap your head around it because it's usually the first thing you're introduced when you're programming. At least it was for me, and I think most people. I mean, freshman level, sophomore level. Hardest thing obviously is being recursion. Recursion isn't really a very common, I mean, construct for me personally, unless you, I don't know, unless you program. I really don't think of any other areas in life where you use recursion, at least purposefully. Maybe you do it by accident. But listen, enough about that. I'm giving you a little bit of a who's who about humanity and everything. But listen, I got my nice program. I got Hello World running. Let me see. Hold up. Let me make sure it says Hello World. Tower.java. Yeah, save it, please. Hello World. All right, thank goodness. Always got to make sure that's working. Now, Tower of Hanoi, from a programming perspective, like I said, it's not crazy. Nothing crazy. But you gotta think about it a little bit. As you can see here, I just have a basic void method. The idea is that you have n number of disks, 1, 2, 2, 3, 4, 5, n. You got the start pole, the temporary pole, and the end pole, or stick, or whatever you call it. These things, these little destinations for your disks. So with every recursive method, sometimes I think with the recursive method, it's good to just put like a template, even if you don't know what you're doing. I mean, there's been times where I'm going, what's going on with my life? What am I doing right? What am I doing wrong? Listen, don't worry about it. There's a template, usually. At least for this problem. If else, all right, if n's 1, you're going to do something. If else, you're not going to do it. And I think it helps even more if you try to do this problem of moving the disks with just one, if it's just one. So let's say we have A pole, we have B pole, we also have C pole, and we only have one, right? If n is equal to 1, I don't know what happens if it's more than 1. I have no clue, but if it's 1, what are we going to do? You're going to take it, assumingly everything starts on A, you're going to take it and you're going to put it to C. Now the way I have the method set up is that you have the start A, temp B, and C. So, you could, if you're actually using like an array or something, you could actually kind of move values. I don't think that's necessarily for this because it's essentially just for the point of demonstrating how amazing I am that after so many years I can finally do a freshman level problem. So let's see. Move A, or actually start. Let's do start plus. Move A to end. We're going to move it to the end. Okay. Actually, this is a string, not a word. So move A to end. And that's it. If n is equal to 1, move start to end. So I just have 1, it goes in the method. Move A, because I assigned it as A, to end. I mean, it's obviously, that's the easiest part. Now, let's think about it if it was 2. If it was 2, and again, like I said, with recursive problems, there's sort of kind of a template you can go with. God forbid if you can't think and you feel like you're under pressure, it's a safe bet that some way, somehow, you're going to be decrementing n by 1, right? And there's only one place where n occurs, so let's see. We're going to do move n minus 1. So that'll take us from 2 to 1 and actually help us go on with our life. If we're at 2, we're pretending that it's 2. If n equals 1, nope, it's 2, else move n minus 1, okay. But where should we move it from? I guess we're still at start. We're still going to be at start. There's still stuff on start that needs to go to the end. But if there's more than 1, 2 or more, at least at this stage, you want to move it from start to the middle. You don't want to go to the end because what you're trying to do is trying to get the biggest one at the end. So you basically have to use, you actually have to use the temporary pole now, and you also have to use the end pole. So instead of the temporary pole being the middle pole, because think about it, right? I want to move this to the temporary pole. So I'm going to go ahead and say that the temporary pole is now the new end pole, because that's my goal. My goal is to move A to B. Whatever's on A to B. That's my goal. I don't want to move it to C. You could move it to C, but I personally think it's better to use the temp pole. Just easier to think. I mean, you move it from A to B, and then from there well, let's not get ahead of ourselves. So now I have move n minus 1, start, and temp. So it's kind of like the same thing as up here, except I switch temp and n. And this is one of those problems where, like, you've seen it so many times, you've heard it so many times. It's very easy to not think and just go along, like, if when I'm typing this, instead of thinking, I go n minus 1 start, switch temp and n. You know what I mean? Kind of, you're thinking, but you're not thinking. So now let's see. This is the magic of recursion. This is a function call. Let's put that in right here. Function call. So now that's a function call, okay? Now n minus 1, 2 minus 1 becomes 1. So here we go, going back in the method. Now n is 2, temp has become C, end has become B, because as you can see here, this end is equivalent to C, temp is equivalent to B, okay? So we have 1, if n equals 1, yeah, n is equal to 1, move, start never changed, start is still start to end. End did change, end changed to B. So we're going to move A to B. That's pretty much it. That's all. We're done. Because this is a void method, there's no returns, but, you know, we'll go to the return, do whatever, and then you're done. So now that's done, right? This is done. We're done with that. And basically, this would move something in memory, but in this case, I'm just printing something out. So now, function terminated. Now we go back. Kind of think of recursion as kind of like parallel universes. We went to this universe where n is 1, and end was temp, and temp was end. Now we're going back to the regular universe. Now, in this universe, we still have the problem that, okay, we moved the one disk to temp, but we still have the big disk that we got to move to the end. So it's quite simply, I mean, really, all you have to do is move the disk from A to C. Because think about it. You have two, right? You got one disk on top of the other. They're both at A. You now successfully moved one thing from pole A to pole B. And now you could basically just take what's on pole A, because you know it's two things. Even if it wasn't two things, you'd have to move that to pole C, because it's bigger than what you just moved. Because one of the rules of Tower Hanoi is that you basically can't have smaller things below other bigger things. And you can only move one thing at a time. So let's see, system.out.print line. Now I'm going to move start, which is A, to end. And in this universe, again, you got to remember, sometimes you get confused. You go, whoa, where am I? What's going on? Don't worry about that last function call. We're done with that. It's over. In this universe, n is 2, start is A. This has nothing to do with any bearing. We're here. The temp is B, and the end is C. So we're moving from A to C. Okay? And then at this point, you're pretty much kind of done. All you have to do is, you can do this if it was just 2. If I knew it was just 2, it would never be more than 2. Then I'd go da 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 da. I'd go. Might as well copy paste this, huh? Save a little bit of time. We'd do that. We'd go da 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 da. Move from temp to end, and you'd be good. You pretty much would be fine. But there's a little problem, and that problem comes with numbers bigger than 2. But hey, good news. This works for numbers 3 or larger, so this is pretty much the last case you really have to worry about. So let's say it's 3. Okay, 3. You go in, n minus 1. You become 2. Start is now going to still be A. Temp is going to be B, and then end is going to be temp. So let's do this. Sometimes it's good to do this. 3, n equals 3. Let's do this. Temp equals C, and then for, well, actually, this is incorrect. This would be for n equals 2, temp equals C, and n would equal B. Okay, so now n equals B, there you go. So now 3 minus 1, that becomes 2. Let's go in. We're going back in the method. If n equals 1, nope. So then 2. So now we're going to, 2 minus 1 is 1. So let's do this. Let's do, when n equals 1, what are the parameters? Start is still start, but you're swapping temp and end. So essentially temp becomes B again, and end becomes C again. This is important just to kind of remember where you are, what are you doing. Honestly, recursion, personally, once you get a little bit on and on, you kind of get used to kind of thinking about the end game, thinking about where you're going and not where you are, you know what I mean, kind of, sort of. But for n equals 1, temp equals B, end equals C. So now n is equal to 1. We went in as 3, boom, function call. We went in as 2, boom, function call. When n is 1, boom, base case. Now we're moving A to C, right? Because end is C. So we're moving A to C. All right, and now we're going to go ahead and return. And again, we're going to do moving, because now this is the 2 universe, right? 2 universe. Where move, we're going to move 2, we're going to move A, start is still same, A to B. Because that's what it is in this universe, kind of, sort of. And then the function ends, and then basically you would do A to C, but then you're not done. You're done with the functions, but you're technically not done. So what you need now is to kind of realize that, okay, I took care of the case where there's still things on start that need to be moved, right? At least with 2, but now with 3, you're faced with the problem that you have stuff on temp. You still got stuff on temp, and you got to move it to C. It's got to go there. So the best thing to do is to kind of think of temp as the new start. Think of end as the new temp. And, well, actually not end as the new temp. You still want it to go to the end. So temp, you could use start as temp, basically as a buffer. And then end will be end. And now this pretty much should complete it, and maybe I should just run it just to let it go through. I mean, when in doubt, why think, let it go for you. So let's see. Maybe take out like a couple of coins and do this, because sometimes it's easy, you know, just to visualize things. So I have a quarter, I have a nickel, and I got a dime, so I'm going to pretend that I'm moving things. So let's see, from move A to C, so I'm going to take the dime and put it to C. Move A to B, so I'm going to take the nickel and put it on B. Move C to B. Okay, I'm moving the dime from C on top of the nickel to B. That's a valid move. Move A to C. Moving the quarter, the biggest one, to C, the last one. That's a valid move. Move B to A. Taking the smallest one, moving it to the A. So now I have, at this point right here, move B to A. At this point, I have the dime on the first pole. I have the nickel on the middle pole, and I have the quarter on the right pole. So everything's pretty much ready to go. I just need to move the nickel, move the dime. Hopefully I did it right. Move B to C. So I move B to C. The nickel's on the quarter. Move A to C. Move the dime. The dime is now on the nickel, which is on the quarter. And there you go. It's done. This also works if you had even more. Maybe if I had a penny. Let's see if I have a penny anywhere. I don't think so. I'm broke. I can't even spare a cent. Okay. I'm back in action. I got the cent. Let's see. Now let's do it with 4, right? Let's do it with 4. Let's do it with 4. Should work with 4. Should work with 3 and above, if I remember correctly. Kind of makes sense because you're taking care of you're taking care of the start, you're taking care of the middle, and there's really nothing else to take care of after that. If there was 4 poles, then maybe I would need another step. Let's say do that. Okay, let's start it. Let's go ahead and boom. Here we go. Fun for days, people. By the way, fun fact, this is the recurrence relation is 2 to the power n minus 1. So 2 to the power 3 is 8. 8 minus 1 is 7. That last thing that I did where it was 3, it took 7 steps, right? So let's see, let's play that. It took 7 steps. So maybe it's good to have a Let's do this. Let's do a static int count. Static. Let's do static int count. And we're gonna do every time you move something, you're gonna go count plus plus. All right, and then we're gonna put count right here. Let's do this. Count plus. All right, let's do push that. Let's do count plus. All right, we gotta do count plus plus. Okay, as soon as you're done, you do count plus plus. Or should it be count plus plus and then move? If I'm starting at 0, yes, but I'm not starting at 0. I'm gonna do it count equal to 1. Equal to 1. Hopefully this will be right. So let's see. Should be 1, 2, 3, 4, 5, 6, 7. 3 again, and what do you know? 1, 2, 3, 4, 5, 6, 7. So as you can see, this takes 7 steps. My point being 2 to the third, 8 minus 1. So now if I do 4, 2 to the fourth is 16 minus 1. So this will be 15 steps. Very considerable. Very large. The big O of this, if you've taken data structures, is 2 to the power n. Very large, extremely large. Bigger than fucking any n to the constant. Part of my language, I'm sorry, but these big numbers get me flustered. So let's see. We're going to move A to B. So we're going to move A to B. We're going to move A to C. We're going to move penny to C. We're going to move B to C. We're going to move the dime on top of the penny. We're going to move A to B. We're going to move the nickel to B. We're going to move C to A. We're going to take the dime and put it on top of A. That's valid. Move C to A. Move C to B. Move C to B. This is also a valid move. Move A to B. So now we're going to move the dime on top of the penny, which is on top of the nickel. Yeah, that's also valid. Move A to C. Okay, we're moving the quarter to where it needs to be, the final place. Move B to C. Okay, we're going to move the dime to C. Move B to A. We're going to move the penny to A. Let's see, move B to A. Move C to A. We're going to put the dime on top of the penny. That is legal. Move B to C. That's legal. C, move B to C. Move A to B. Put the dime in the auxiliary pole. And move A to C. We got the quarter, which is under the nickel, which is under the penny. And then finally move B to C. We move the dime on top of the penny. And there you go. We've got our tower. As you can see, it's not that hard. But you really gotta have a strong understanding of recursion. Be comfortable. Be confident. With any math problem, with any problem like this, it really helps to just, take it easy. I mean, there's, stupidity and intelligence. They're cousins of each other. Sometimes you got to be, you have to do something stupid in order to be intelligent. I mean, the first time I did this problem, it took me a little while. It took me, even when I got it working, I was like, why is it working? I don't get it. The thing that tripped me up is like, why do I need this? And then I had to really think about it and kind of played out in my mind and say, hey, you know what? There's still things that is on the first pool. I need to take care of that. I need to move things from temp to the end, using start as a temporary. So I think that this problem is a good example of recursion because it kind of gets you familiar with it, not only with the problem, but just how great it is to solve something. Time complexity isn't the best, but let's be honest, how exactly are you going to do this without having it be so large? Let's see, let's do something really large. Let's do 10. 2 to the power of, well, you know what, maybe not, that's a little too big. Let's do 2 to the power 6. So it's 64, so it'll be 63 moves. Let's do this, and let's go. 63 moves. So very large, grows very quickly. As you can see, it went from 15 to 63 with 6. Very kind of simple. If you look at the method, look at it. It's not a lot. It probably would look even simpler if I didn't put this note right here. But yeah, that's pretty much the gist of it. If you have a problem with this, hopefully you can realize that, sometimes you got to think, because you might know the answer now, but understanding it and knowing are two different things. So take the time out, take a little break, get a little tea, a little bit of crumpets, and enjoy this recurrence, not really relation, but more of a recursive method.